All right, everybody. Hello, my name is Rebecca Lindell, and I have the pleasure of being the chair of the Physics Education Research Leadership and is it Organization Union? I never forget.
Organizing Council.
Organizing Council. And I have been working with this. And one of the things we introduced this year is really exciting to us is these new community conversations. And these are sessions where we bring people together. And this is actually our fourth one. So this is our November 2025. We bring people together and so we can actually talk and get to know each other and also hear really great people talk and include us in a conversation. So this week's or this month's community conversation, we're actually being joined by Tim Stelzer, who is a professor at the University of Illinois, Urbana-Champaign, who is actually he's at the Urbana-Champaign. He's been there quite a few years doing everything. And I am going to say he's responsible for such innovative projects like IO Lab, Clicker, or iClickers, and also whatever flipped physics is called these days, working on those projects.
Thinking physics. Is it thinking physics, Tim? Not anymore.
No, it was smart physics. Yeah, the
Smart
publishers
physics,
had lots
yes,
of good
smart physics,
ideas
yes.
about names.
So what do they call it now?
I don't even know. It's a good question. I don't know.
As anyway, so Tim is here to join us, and he's giving a talk to us on lies, damn lies, and
Let me interject a little bit. So Tim was the chair of the committee that was formed by the Physics Education PhysRef, Physics Education Research Journal, to help people write up quantitative studies and review them because of the certain issues that arose related to the publications. And so that's why we invited Tim, who has, really good overview of what is happening in the field, what issues exist, and that's why he is going to be sharing his knowledge. And also, thank you all those who responded to the survey that allowed Tim to actually address the burning questions. Thank you. And Tim, you're welcome.
All right, great.
So let's welcome Tim, and looking forward to a great talk.
Okay.
Great conversation.
Yeah, exactly. Great. So thanks so much for an opportunity to chat with you all. Yeah, I'm not great at Zoom, but so it's first when I look like this, I'm actually looking at you instead of my screen, so I know that's a bit annoying. Second, I've asked if you have questions, like I want it to be a discussion. So if you have questions, you can type them into the chat, and then I've asked Eugenia to just interrupt me when I'm taking a breath or something to say that, because I've just prepared about 6 hours worth of material here. And so it'll be best, like, if you have things you want to talk about, then, just make the comment, ask the question, and we'll talk about it, because that's the whole point here. So, yeah, I want to make the case for statistical sense making. And here's the way it's going to go. I want to start with your comments. So 10 of you took the time to share some insightful comments. So I just want to start by talking about those. Then I want to share Eugenia's wisdom, which means she'll probably never invite me to another talk.
I don't know how to turn off the sound here.
Oh, yeah. Yeah, exactly.
If you could all put your sound on mute, that'd be great.
And then, then I just kind of want to do some statistical sense making. And I thought one way of doing that, so I'm going to, kind of go through some generic examples. And then I grabbed a paper, just serendipitously. It was one that I was reading, and I thought, oh, okay, well, let's just, apply these ideas to this paper. And, it's a very good paper, actually. It's a paper with some really exciting results. And so we can just, apply these techniques there. I want to comment that, after this, there are resources available. And in particular, there's this editorial, I guess it's called, that we wrote up as part of the Statistical Modeling Review Committee. And Eugenia had mentioned this. If you're wondering what that is, this is the committee. And I saw Charles was on the call here, and Charles is the person that pulled this together to try to provide more resources for our community as we start doing, much more sophisticated statistics. And so this is the group of people, and we spent a lot of time coming up with this 3-page paper. So I encourage people to take a look at that. And also if you just, want to chat with me or something, there's my email. We can talk. All right, so let's start with your comments. And I kind of broke them up into, there's sort of 2 questions, about writing paper or reading papers. And so for writing papers, people were worried, am I going to be doing the right tests? Are my statistics, are they going to be sophisticated enough? Can somebody tell me, are you able to see my mouse when I'm doing this? Is it sharing my mouse? Yeah, okay, thank you. If they're sophisticated enough, yeah, I'm going to argue that usually the issue isn't that they're sophisticated enough. It's often that there aren't enough less sophisticated statistics.
I was going to say, Tim, if you could increase the size of your mouse, it's very, very tiny on the screen.
It's very tiny. Okay, thanks. I can switch and use my pen here and just make a mess of my screen maybe then. And so in this one here is, okay, the improper interpretation. I should say that really it's usually interpretation as opposed to usage. And yeah, we don't want any scoring. I mean, especially within our community, the whole point is that we're supporting each other as we learn these techniques, and we're all trying, like we all have the same goal, right? And so so hopefully we can do this in a very supportive way where we're still, being critical and learning. Yeah, I love this one. A qualitative researcher saying they want the deeper statistics. And yeah, I don't know. You'll see what we think after we've talked about this. I'm not sure I'm pushing people into deeper statistics. And this was a really insightful comment. It's like, oh, you hear me talking, or you hear us talking about, like, don't worry about p-values, and these are the things we care about. But then the person that's reviewing your paper says, no, we need these things. And so how do we advance this? This is like a super great question, and we're trying to figure it out. And in fact, having conversations like this is one of the ways, because it is a community journal, and we decide that. Now switching to reviewing papers, lots of stuff about, we all get papers where they're using statistics that we're not familiar with. And so what do we need to do there? And I really like this, causality, because that's been a big issue that comes up. And one thing I want to say over and over again is, like, statistics, you don't get to claim causality because of statistics. So there's not a statistical causal test. And so, yeah, this is always a big red flag when that's coming up. Lots of questions like, oh, do I have to become an expert on it to do your reviewing duties? And I think the answer, I just want to say, in my opinion, is no. And we'll talk about things that I think we should do. But I think we want everybody's opinion, and just because something's using lots of statistics, we don't want to just narrow ourselves down to a small number of people that review it. And here's a similar one. Should I turn it down if I don't know all the statistics? And the answer is no. You should do them. And one of the things that we've talked about is actually having a more formal place on the review process where you can just kind of click whether or not you were able to check the stats or not. Do I need to check the citations for all the statistics? Yeah, no. I don't think that's a requirement. And here one, I really like this. And this is, again, this gets to what I'm thinking about with statistical sense making is, when you hear a bunch of these names, and they say they did it, and you're like, well, oh, okay, but what does that mean? Is that the right thing? And I think that's a place where, as a community, we want to do a good job of really explaining why we're doing which tests. And again, that's going to be part of this sense making thing. The very last comment that came in was this one, which I kind of summarizes what the whole talk is supposed to be about, is what we really want to be able to do is clearly explain and critically evaluate the statistics that we do. So, that captures it all. So that's what I want to hopefully we'll talk about exactly that. So I want to start by talking about Eugenia's wisdom, and this comes from Eugenia's camera is off now, I noticed. Eugenia. Yeah, there we go. Face the music here. Because 25 years ago, I think I heard Eugenia give an aisle talk. And I remember when she gave the talk, I thought, wow, she's a great speaker, right? She has lots of energy and enthusiasm. And she's talking about aisle and she's kind of saying stuff like, oh, this is what science is, and you need people to understand the nature of science. And I kind of thought, yeah, but it's all kind of obvious stuff. And then it seemed like every single year after that, there would be a big thing where there was all this controversy. And it was things that, I thought I had said were obvious, but then in fact, they were exactly the thing that Eugenia had said in that talk. And so, one of the things is that we always want to prove our theories right. But, the first thing she says, oh, you don't get to prove a theory is right. You can only prove that it's wrong. I'm getting you this correct, am I not, Eugenia? I hope she's not saying, no, I never said that. And that's very against human nature. We always want to prove that we're right. But maybe the healthy way to think about it is you can try to prove other people are wrong, because that feels good too. But it's an important thing to be thinking about. And the other key thing that's so important is thinking out, okay, you've seen something, you have some data, you've experienced it. You really got to think about, like, not just what is your explanation, which is for sure right, because that's why you had the explanation, but what are alternative explanations for this? And, this is really at the heart of what we need to do in physics education research. And it's really, really hard, because like there's an infinite number of alternative explanations. And I think Eric Kuo is on here, my colleague, and this was in our paper. I think it's a quote from him, is that as a field, a good measure of our maturity is our fluency in identifying plausible alternative explanations. And you get that with experience, and and new ones come up and we learn about them. So like we don't have to feel bad when we miss one, but we should always be looking for them. And that's going to be a huge part of this. And then, related to that is, you just got to think like, what is the research question you're asking, or what are the claims the paper's making? And these are the things we need to think about as we're writing and reading our papers. So, yeah, so basically, if you know all these things, you're in pretty good shape. And then the statistics is just sort of a detail along the way, I would say. So I've been yakking too long. I'm now putting an image up, and I want people in chat to see if anybody knows where this image is. And then if you do, if anybody can guess why I'm putting it up there. And I can't actually see the chat right now. So it's silent. Nobody knows. Is that right? Oh no, there's 6 new. I just don't know how to use Zoom. Yeah. All right, fantastic. You totally got it. Guima from Demon Hunters. Yeah, and it's anxiety. Exactly, from inside out. Okay, and so my therapist says the reason that I want to show this is because I'm so proud that I saw a popular movie and enjoyed it. But from a statistics point of view, I think one thing that we sort of need to face as reviewers and stuff is not being intimidated by the statistics. And so here's my version of it, is that Guima, right? We see all these words and they are intimidating. And I can tell you that when I review these papers for the Statistical Modeling Review Committee, I'm often intimidated. In fact, you can't spell intimidation without Tim. And so I experienced this quite a bit. But sticking with the theme here, the thing is we can't, like, this will be our downfall if we get intimidated and aren't critical, because we're like, well, I don't really understand all these statistics. We need to make sense of them. And so here, I think I have a little picture here. So here are our heroes here. And the things that we're going to use is, Eugenia's thing, what is the claim? What's the research question going on there? What are the alternative explanations? And then for the statistics, I'm going to tell you that sigma over the square root of n, I mean, that'll carry you a long, long way in your statistical reasoning here. And so that's what I want to do. And I want to make sure, we just don't be intimidated, ask the questions, and we can do this sense making from here. Okay, so I'm going to keep going. And I think for me, one of the hardest things about doing PER statistics is my statistics I learned from doing this pendulum experiment. And, I did it and we used a couple of different lengths and we took a bunch of different measurements and we got data that looked kind of ugly like this. And then sort of the miracle of sigma over the square root of n is we could take this and we could turn it into values where, the average value, and then we could put some error bars on that. And that's the sigma over the square root of n. And that's just an incredibly powerful tool when you have sort of messy data that the orange looks further to the right than the blue. But, you can turn it into this very beautiful, clean plot here, and then you can do modeling. You can fit it, and I can say, oh yeah, the period is 2 pi square root of L over G, and I could probably use this to calculate G or something like that. And this is the model I always have in my head, but I'm going to show you it's a really bad model because people are just a lot more complicated than a simple pendulum. And even when people told me that, I said, oh, okay, people are more complicated, so it's not a simple pendulum, it's a physical pendulum. I can deal with that. It's just a slightly more complicated equation. But that is also not a good model for when we do statistics and physics education research, because people are a lot more complicated than this. And if you see all the things that are affecting students and how they perform on these exams, they're almost all things that we don't know about and that we can't control for. So here's the model I think is good to have in your head when you're thinking about doing, if you want to do the pendulum comparison like I do. It's kind of like you're going to do the pendulum one, but you get to do one measurement with a guitar, and then somebody gives you a different instrument, and you do one measurement with that, and then a different instrument, and a different instrument. And each data point, right, it's a different person, and they're very, very different. And you don't get to control most of the things about them, right? And so you're going to get all these different values for the period, and you're not going to know. And do not hang your string instruments. Thank you. I like that. And, we don't know the moment of inertia. We don't know R for this. And the thing that we control is something like the angle that we, release it from, right? That's the kind of thing that we're going to get to do. And then we do things like we write models and say that the period depends on that angle. Maybe know the mass. Maybe we know if it's a woodwind or if they read the bass clef. And then we get some sort of fit like this. And, this fit, right, is very, very different than fitting for the period of a pendulum, because we're really not controlling for everything. And that's one of the reasons these are so complicated. And whereas with the pendulum model, there aren't very many alternative explanations, right? You can decide if it's a square root or not. You can decide what G is, but there aren't a lot. But here, there are just tons of alternative explanations for most of the data that we get. And that's basically where a lot of the complication comes in. All right. Do we have any question or comment at this point? I feel like I've been talking a long time.
Not yet.
No questions. Okay. Everybody go get their chips.
Yes.
Okay. So basically the way we deal with this is we have to average over all the different instruments, and it makes a difference which instrument it is and things like that in order to make our measurements. So I grabbed some old data here where it says treatment and control. It's like a pre and a post test for 200 different students here. and just kind of showing how we do this data. Here it looks, very much like the pendulum data that I showed you here. And basically, again, when we say this plus or minus here, it's just looking at the standard deviation dividing by the square root of n there. That's all that number is coming from. But again, it helps us a lot. And so now I can take these pre and these posts and I can plot them in this nice way, just like I did before, and kind of decide like, was there, did my treatment, did the activity I do have any effect? Yeah, and it looks like it's about a 2% effect. We've been talking about moving to 95% confidence intervals. And so just to remind you, like all that means is you just take this standard error and you multiply, well, technically by 1.96, but you can multiply by 2 and nobody will catch you. And then, you can say, well, is this just a statistical fluctuation? And, and that's this plot here where I have the 95% confidence interval that you're showing there. And notice that it doesn't align with 0. So yay, we have p less than 0.05. And so, that's kind of what we're doing with the statistics, to get the data out. But you can see that there's this huge variance here, right? Things are changing by, from around 70 by sort of plus or minus 15 or 20 points here, because we have so many different students doing this. And so since I know this is a pre-test and a post-test, I can actually reduce these error bars, because instead of just taking these as two sort of independent measurements here, I can use the fact that actually these are the same students doing both tests. And so I can instead just plot the pre minus post here. I don't know if it looks a lot better to you or not, but it has a smaller standard deviation. And so then my error here is smaller. And you can see when I replot this result, the mean didn't change at all, but the error got reduced here because I used the fact that these are the same students taking it pre and post. And so I that makes intuitive sense to me. I can see how that's working. One thing that's a little surprising to me, but that's true, is that instead of doing pre minus post, I could do the thing called linear modeling, which people do a lot. And is a thing that shows up here, whereas I can actually fit a line to the pre minus post. And so in this, and by doing that line fitting here, doing that prediction, it's actually better than just subtracting the two. And if I do that and do that modeling, I actually get a smaller variance. So all this modeling stuff is doing, and so far in what I've described here, is I'm not changing n, right, the square root of n that affects these things, but I am changing the variance by trying to, include other factors. In this case, just the one other factor, the pretest. And you can see, well, it's not a huge difference, but in each of these, I'm reducing the variance. And so, this one simple idea, the square root of the standard deviation over the square root of n, and then understanding how modeling can reduce that variance and what one can expect, is a thing we can use to do sense making for statistics, even when people are doing pretty complicated statistics, and just make sure that, okay, this all seems reasonable and I understand what's happening. All right, any questions or comments so far? Eugenia?
No, not yet.
Oh,
Yeah, I got a
okay.
question. I got a question.
Please.
So I'm gonna out myself for showing I don't know anything, but 2 slides ago, you had a slide, yeah, that one, where I didn't get your hooray, p is less than 0.
Yeah.
Is that easy to explain how you know that or can tell that from that?
Yeah, thank you. That's a really good comment. And so, so because I chose to plot for my error bars here, I use 2 standard errors. So instead of being 0.8, this is actually 1.6. that means it corresponds to a 95% confidence level. And so then when I did this subtraction of the two, and I did these error bars correctly, this 95% confidence interval, it's not touching zero. So that means that the probability of it being a statistical fluctuation is less than, and the 0.05 is just, 95 plus 5 equals 100. And so since I used a 95% confidence interval, then I can say that since I don't touch zero here, P is less than 0.05. But also I was trying to be a little bit...
But if you did...
If it did touch, then P would be greater than 0.05 and it wouldn't matter. Right? Because it doesn't, it doesn't matter. We're not claiming discovery of a particle or something. The thing that's interesting is the value is about 2%. And so probably I'm going to say it wasn't worth the effort for this 2% change. So
here is a question though for you.
Thanks.
Patrick Banner from Swarthmore. I know this is a common method, subtracting so as to reduce variance, but are they the same students? What if a student, say, got on anxiety meds from the pre to post testing or had a family member pass away, etc.? We always have to make some assumptions in the statistics that involve humans, but it's perhaps useful to just state those explicitly, whether it is not too many students have major changes from pre to post, or we're averaging over it anyway, or whatever it is. Is that valid?
Yeah, so you're 100% correct that the same student taking the same test two different times can definitely score differently. And that's one of the reasons when I did this, when I did pre minus post, you could imagine a situation where it's just a huge peak at everybody just got 2% better. But that's not what we saw, because the people are different and things change throughout. And so I don't know about, it's a good question about explicitly stating it, because it's always true. And that's why I'd like the example of the pendulum, where we're just using different instruments all the time. And so, we're usually can't control for the most important things. So I think I exactly agree with you. We are averaging over them. That's 100% correct. But there can be systematic effects, and we can be fooled by them. So I think I'm basically agreeing with your comment, if that's okay.
Thank you.
All right. Thank you. Yeah, and then this last thing, where by doing the linear modeling here, and the nice thing about linear modeling, it doesn't have to be pre-post. In fact, most of the time it isn't. Oftentimes we're using things like GPA or FCI score or some ACT score or something like that to try to reduce the variance and kind of be able to focus more in on the variable that we are controlling and understanding it. All right. So the next thing I wanted to do was just look at a paper as an example, and I don't think David or Cassandra are here. I just want to start by saying, I think this is a great paper, so I'm not pulling up something, to rip it apart. And I like the results a lot, but also it's true of any paper, right? You can always comment on things and say, oh, there's something here that would have been nice additional to have. So that's the way I was going to step forward and just apply this here. So looking at the abstract, this paper makes three important claims. First, they did a class where they switched the course in a sense where they didn't do complicated calculations. They went through the material, but really at a conceptual level first for the first half of the class. And then the second half of the class, or the last third of the class, maybe it was, they went through and, and did the harder math stuff with it. And they have an amazing result from that in making that change in the order, they found out that they no longer saw a difference in final exam scores between the majority group and underrepresented ratio groups. And I did that in green because to see, like, it seems like a really strong and amazing result. And the next one is it's two different studies in the same paper where they had a class, four different sections of a class where they gave students the option of doing a retake on their exams. And they found out that when they did that, they got rid of, there was no longer a difference between the male and female course grades at the end of the semester. So that's a nice result. But I'll say this study, I think there are more alternative explanations for. And then the last one is that the analysis indicates that the demographic grade gaps can be attributed to course structure rather than student preparation. And so here, maybe I'll take a bit of a hot take. I certainly agree with this conclusion, except for, I don't think this is something that the statistics are telling us. I mean, I think it's a true statement, but I think this is an example where it's not something that we're learning it from the statistics. I think this is a separate argument that we want to make here. So I was going to go forward with these, unless, are there any other questions or comments?
Nope.
No. All right. So here we go. So here is the plot. This is the first plot for the first claim that they're making. And so first I'll say, like, this is a great plot. I really like it, but I'm just going to say something I would like better is, this plot here, I would love to just see the scores, right? This is a final exam score, and I would just kind of like to see like 78% or whatever it is. But they're refining it a little bit. First, they're normalizing it by units of standard deviation. And so to me, this makes it, I don't know, a little hard to understand, but basically I use my intuition, and almost always, if you have a 100-point exam, the standard deviation is probably like 10 or 15%. And so we can see there's a pretty big difference here between these courses in gray or yellow, tan, whatever color that is. They're down by like 10% compared to the course in blue, which is the concept first course. So really, really huge difference here. And they shared numbers with us. So for me, one of the first like sense making things I do, I mean, I love the plot, but I just kind of want to make sure, like, is it reasonable that they can measure something this accurately with how many students? I mean, 150 students is a lot, but only 13% of them are underrepresented. And so, if I do that calculation, there's only 20 students basically in one of these things. We're subtracting 2 scores, but one of them only has 20 students. And so we can just do this test here and just say, well, square root, let's see if I can find this here, square root of 20, sigma, and it seems like we should be sensitive to about 0.2 standard deviations. And you can look there, and that's what it is. Okay, so like, to me, this is an example of, like, I don't know, just, I'm calling it sense making. Just like, okay, these number makes sense. They had this many people. They did the final exam. So yeah, this looks totally legit. And we can do the same thing with these other ones here. So like, I don't, like, from a stats point, like, this is just very clean. And I just say, like, yeah, that looks real. The error bars are there. I mean, this does not look like a statistical fluctuation, and it looks like a huge deal. Again, I wish they had percentages here, but this looks like, maybe 10 to 15% difference in how these students are scoring on the final exam, which is crazy good. But we need to think, like, what are some alternative explanations? Like, how else can we explain this? Because the point is, we want to be critical about this. We want to know, is this the only explanation? And so for me, one of the first thoughts is, well, maybe these are different teachers. So here, these are all our bigoted teachers who are awful, and this is our wonderful accepting teacher. And, so it really isn't about the order, it's about the professor. But here's a great thing about this paper. These two courses on the same semester were taught by the same teacher, right? So this is crazy good. It's the same professor. And if I understand it correctly, they were mostly using the same slides. They just changed the order of them. It's probably can't be 100% true. But so this is a really, really strong result. So I'm excited about it. What's another alternative explanation? Well, another alternative explanation is they're different students. I mean, they are different students, right? It's not the same students. And 20, and it could be like the timing of this course meant that all the students that took this one were in some, special advanced program. And so that would be something that we'd want to check for, that maybe we don't think that this is really coming from the concepts first. Maybe it's just coming from the time that lecture was happening at. Okay. And so this is an example where in the paper, what they did is they modeled, right? They had some information about the students that were taking the course, like before they went into the course, and then they could do some modeling for that. And again, a thing I really like about this paper is they did a nice job where they started actually with the modeling, just doing the very simplest thing, just doing the model to reproduce results that in general, there was a difference between the underrepresented and the not, and then adding it into a single model here. So you have the result for the concept first people, and then the underrepresented people in general, and then this interaction term for if, concept first helped them. And so from these data here, they're able to just reproduce these plots here. I didn't put the numbers up here, but they basically give those numbers. And then they go ahead and add in two extra terms. One to control for what was their calc score, and then they took the FCI. And so they had both of those things that they could account for. And that's what this result here is on the right. You see in both cases, the underrepresented students, essentially they got a boost from this because their calc and FCI scores were lower. But, the boost is basically the same, and the result is robust to this change. So to me, this is like just a crazy strong result. And I don't know. Oh, and one other thing we do is I try to look at the error bars. So this error bar here, because now we're controlling for the incoming preparation, we'd expect it to be lower. And I just put it here, and you can see that the variance was reduced here by doing that. So that's one of the things I'm kind of talking about for sense making. Any questions or comments on that?
Not yet.
Oh my gosh. Okay, so I don't know. I must not be getting right at the things people are concerned about. So I mean, maybe you're hoping for something more complicated than this, but this is very useful, and you'd just be surprised how many things you can find by doing this. And so I got to tell you, I have no other alternative explanations. Maybe I'm not very mature in the field. The only thing I'm left with is there's two things. I mean, it's still just 20 students. And, maybe there was something else special about those students, right? That isn't included in there. But this is I don't know. I mean, looking at results, I know Charles is on the call here, he was before. Uh, like you just don't see results this good for a problem this hard. And in fact, the only concern I have now is like I haven't seen like a follow-up for this particular thing that that they did it a second semester and got the same results or something. Because, you know, this is a pretty big deal. And no, are there people that have studied this paper and like know what I'm missing here?
I
No.
think, Tim, this is
Yeah.
one of the issues with all our studies. They're done once.
Yeah. Yeah,
So we
exactly.
need to do it many, many times to have the reproducible result. So is it
Right.
a reproducible result or not? And so that's another big issue that we, as a field, we're satisfied with one intervention.
Yeah.
And we publish it. So
Yeah. Well, I mean, I'm
that's my
happy that this was published, but I would like to see more, I would let, presumably at the place they did it for another semester, I hope. Um, the other thing that I don't know, and I think when I read the paper, I convinced myself that I would like to see, I really wish I had the raw scores here because these things um, end up getting normalized here. And when they did the fits and stuff, they normalized them. And so somehow you worry that there's something being hidden in this normalization. But but yeah.
uh,
Okay.
Tim,
Go ahead.
here's a
Yeah.
question from me. Is it
Thank you.
generally a good advice to share the raw scores before
Well,
normalization for any purpose so people don't have this uh worry? Because
y-
I always feel the same that I want to see the scores before I want to see all normalized and massaged stuff. Is that
Yeah,
advice?
exactly. That for me, that's a very strong statement. I feel like, every time you do something to the data, you throw information away. I mean, you can argue if it's relevant or not. And so I would say yes, or at least in in the appendix, like maybe you feel like it's too messy and it messes with the flow, but just to let people who might have like the authors might realize like, oh no, these scores were 70% and they were the same. Like they know there's not a problem, but the reader doesn't necessarily. So I'm not trying to say there is a problem. It's just that like we don't have the information to really to rule out some of these alternative explanations that the data is there, like they know, but we don't know.
Uh, I just
Yes,
have one brief
David.
comment. Um, you can control by using a model, but a model is a model.
Yes.
And there are other models that are possible, other models that are available. And the fact that this particular model, as we see in the data here, the effect is preserved when using it to control it, does, does not by any means exclude other models that may be used to adjust the data and which could give a different result. I'm not saying that they do. I'm just saying that it's just something to keep in mind. A model is a model, and there are multiple models possible. That's all.
Yeah, that's absolutely correct. And so for me, at the end of the day, like I have this result on the left that the students are scoring the same, and so without doing anything with the model, right? This is just the only thing they've done is well they normalize to the average for the whole class. So that's one of the things that I'm not happy about. So, it could be that I mean, I know it's not true, and I'm pretty sure in the paper it says somewhere, but it could be that like, oh, everybody just got a 40% and that got rid of the gap, but nobody learned anything. Um, but uh, um, but that's not the case. And these people, they all took the same exam too, by the way. So they really did a good job.
Uh, there's a
Yes.
comment from Eric Kuo. just agreeing for readers, reviewers to do this kind of sense making Tim is describing, they need more information than your final model.
Oh yeah, thanks, Eric. Yeah.
But I think overall, your message is, I'm
So you're
sorry.
muted.
Yeah,
You're muted.
that you need to make sense of the presentation that they did, because we see the presentation, not the
Right.
real analysis. We see the result of it, right? But you also need to see whether this presentation matches the data that they have.
Right. Right. Exactly. And so I want to look at the second one here, which,
Sorry. Before
yes.
you move on to the next one, I'm just wondering, how would you how would you go about presenting the raw data in a case like this, where I think it can be more straightforward to do a comparison of raw data if you're comparing two groups to each other, but when you have, in this case that you're showing us, there are four groups. Each of them has their own distribution that can get difficult to understand when you're visualizing or reading something like that. How would you present that in a way that would
Brilliant.
not be an overload for the reader?
Yeah, thank you. Like that's a brilliant question, and it'll have different answers, of course, for different studies. Like for my personal opinion on a first try for this would be there was no need to normalize these. Like I would have loved to have seen at first a plot that just had, the score for the underrepresented students and the score for the overrepresented, not underrepresented students in the concepts first, and then a similar thing here where we would see for the underrepresented it would be here, and for the control here, because then I can do a direct comparison across this way here, and I could do it I could do that for all four courses. And then probably in the appendix, I might provide something like the distribution of these scores, right? Because I agree, we're going to assume that they're sort of fairly normally distributed. And so you can just have that, to confirm it in the back. But here, you can do it. It doesn't take that much more. I agree that, this is not a bad plot. It's just that I want this one too. This is hiding a bunch of information.
Tim, there are two comments here.
Yeah.
One is by David Lowe about the challenges with reproducing results in social studies, sciences, including PR, because you don't get as much credit as you get
Yes.
for the new stuff.
Yes.
And then Dana wrote, I agree, this was an interesting paper that came across my desk. And they put the link to it, and I looked it up immediately. And this is Values Affirmation Replication at the University of Illinois by Brian
and
Gutman
me.
and Tim Stelzer.
Yeah, no, I mean, right. And that one that we were trying to replicate, though, it's interesting. If you did this sense making thing for it, you would have seen a bunch of red flags on that original paper that we are trying to reproduce. And so I learned my lesson the hard way. But yeah, I mean, that's a good point. And I think as a community, but we can, Charles is going to know all the different things that came through, but my guess is if somebody just did this a second semester, like these same people did it a second semester, and they got the same result, it would be a short paper, but it should get published. I mean, I can't, I don't know. Charles, can you tell me, would there be any problem? Would that get rejected?
Yeah, well, I mean, it's the devil's in the details, right? I think if you framed it right and really
No,
focused on the importance of that finding, then yeah, I think you
yeah,
could.
yeah, of course. Okay, yeah, it has to be an important finding. But I mean, like this one here, to me, is I don't know, huge.
And I will say I think it's exactly right that there's so many findings that are based on one paper that are not replicated, and that's a problem in the field. It would be much stronger if we had a an ethos of, oh yeah, it's valuable to replicate these, and particularly, I mean, it'd be even better if somebody else other than the original people did it, because that's the real
Well,
the real
yeah,
sign
yeah.
that it actually works somewhere else.
Yeah, that's even better. This particular change, I mean, seems like a pretty big change, and so I would want the place that was doing it to reproduce their results. But I mean, you can just contact it. I could just contact them, right? They've probably done it and just haven't published it. I want to move on to the second one, which is a much smaller change. You're just offering retakes, and it's getting rid of the gender gap. And we're going to do the same thing that we did before. We're going to go ahead and look. And so, just to be clear, we're plotting something a little bit different. We're plotting the final grade for the course. And it's normalized to 0 here. And oh no, this is the gap. Sorry, it's not normalized to 0. Sorry, so we're subtracting the 2, so we don't. They're normalized. They said they have a standard deviation of 1, so it's actually the GPA. It's like just using the letter grade and converting it to a number. And in this case, if we do the sanity check for the stderr, which I'll tell you, to be the honest truth is that I did this for the first time yesterday. And I did this number, and it's 0.09. And it doesn't match with what's there. Okay. So, yeah, I'm not going to say that word out loud. I think it would get edited anyway from the YouTube. It's an intimidating word, but basically, the standard error is still sigma over square root of n, but the sigma for this group is not the same as the sigma for this other group. And just, to be careful here, notice that we're comparing 13,000 students. So this is tons of years of data versus just 1 year's worth of data. So maybe it's okay, but they have different standard deviations. And this would be a warning sign, right? It's not what you would expect. And so you can move forward. But otherwise, we do see a case where it's a grade difference of 0.2. I don't worry about the control or no control, but the retake and the no retake. And we see here, there's no difference in grades between the male and female. And for the other courses, there's a 0.2, so a fraction of a letter grade. And so one of the things we should do is think about, what are the differences that could be causing this? And I was going to give time to do it, but we're almost out of time. And so I just want to list some standard ones that we could do is, again, different teachers. And there definitely are different teachers in this case because we're going over a huge time frame. And so, it could be that this teacher is just really, really good at dealing with that. They are also different students. Here, the paper will do the check to see if that explains the difference, and we'll see that it doesn't. And the other effect, and I'll say, like, almost always when I see effects that reduce a gap, the easiest way to do it is to just hit the ceiling. If everybody gets an A, then there's no gap. And I would say that that can happen 2 ways, right? That can happen the good way, where everybody has just learned more, and that's great. So everybody got an A, and that's the ideal scenario, right? It can also happen, and you know, this would be a warning, if you let people retake and only people who did poorly retake, you're naturally going to get higher scores. And so it could be, you know, in that sense, it might not be more learning. And so that would be a concern, that essentially you're getting a higher grade without higher understanding, and the ceiling effect is coming in. And so we can look at their analysis, and when they do the fit here, this was just an example to see reading these things. If we look at the grades that people got when they weren't given the retake, we see that they're you know, close to a B, but they differ a little bit, like 2.8 and 3. And so that difference there is this gap of 0.21. That's this gap here that we're seeing. When we look at the retake, if we read these coefficients off here, the men's with the retake, they're getting this bump of this 0.31. Okay, so that's this retake value. And then the women get that bump, and then they have these two extra terms in 0.34. And so we see that the gap here is much smaller, but also like these numbers are just a lot higher, right? And so notice that we're looking for a difference of 0.2, but in fact, the difference between these two courses is 0.4. So it's down here. So it's sort of an interesting, I don't know, a concern, like, to me, just that, like, I would say the point of this paper, a bigger point of this paper is, wow, you know, students did a lot better, like all students did a lot better, right? They did better, like twice as much as this gap that we are worried about, we got an improvement for. And so that would be nice. Like if that was the case, that's fantastic. But then, you know, when I tried, when I tried like modeling like what these grades would look like a 3.4 average. So here's the 3.0 average distribution, like kind of what the grades would look like. But when you go up to like that 3.4, you can see, you know, you've really hit the ceiling here. And so probably the reduction in the gap is the ceiling. And so then I feel like the interesting question one has to ask, like, you know, did they learn more, or did we just raise their grades because we gave them a second chance? And so again, my example of, you know, statistical sense making here for doing that. And I think I've burned through all my time. So I'll stop before.
Tim, question, but isn't it, it's just for me to understand. I always thought that that this data collection and statistical analysis gives you kind of a pattern, but the explanation comes from qualitative studies when you are asking questions. And so unless you're asking those questions and interviewing and observing people and collecting qualitative data, you can't have an explanation. You can't have a mechanism.
Yeah. Thanks, Eugenie. Yeah, of course, that's a super good point. Is that yeah, you know, our ideas for what's happening, you know, for the ideas that we try, you know, definitely come from qualitative or just our observations when we're getting tons of data coming in compared to the limited amount that we get from an exam. And then the statistics will tell us patterns. I feel like, yeah, so I know the prior talk was on qualitative, and, you know, absolutely critical to the field's health is that we continue doing that. You know, but the quantitative, of course, also has this role of being able to, you know, check, you know, we can disprove these theories or some level of these theories. We absolutely can do that. And, you know, and hopefully, like I said, with this, you know, this first study that we have, you know, I would like to check it more, because, you know, if we can run that multiple times and see that same result, it's it's going to be pretty robust and it's going to be a very, very strong result. So failure to disprove it really gives it a lot of credibility, but we need to do more attempts on it. Thanks. Great. Yeah. And so, I'm out of time. My last statement was just that, and I think it was kind of along the lines of David Meltzer's comment, was that, there's sort of this comment that even if you control that it's a structural problem, because even if we control for their calc score, there's still a deficit. And I don't think that's a good way to make the argument, because it kind of suggests is if I can come up with a test that the underrepresented students score worse on, then I can say it's not a structural problem. And so, the fact that you don't have the data showing what the difference is between the people shouldn't be the criteria, or having the data shouldn't also be the criteria for whether or not your course needs to be able to create equal outcomes for everyone. And I think the community is talking this way a lot about it, and I just agree with that. All right, well, let me click through then and just show my last slide, which is just a reminder that, I really encourage people, start with simple, and the paper should include simple, and that should show the main result. And then when you do things more complex, like doing modeling and stuff, you should argue, what are you trying to, why do you need to do that more complexity? Is it just to reduce some variance? Is it because your groups aren't equal? Is it, it's basically because the data isn't clean enough, because you couldn't do the ideal experiment. And so you really want people to explain why they're doing that, and then make sense. Like when they did something more complex, did the result really change, or did the variation just went down a little bit? Because if it really changes the answer, then we have to lots of concerns, because as David said, that means there's something, it's all about your model. And if your model is off at all, it's changing your answer. And the other thing, just when we're doing these reviewing and thinking about the statistics and stuff, we really want to practice, even when we believe something is correct, oh, this is a really good thing to do, the way we make the case for it stronger is by thinking of the plausible alternatives, and then people can do studies to eliminate those. And that's what will make the result stronger for doing it and figuring out how it can be tested. And then just, a final note, since people here are, concerned about doing the statistics in there, is that, Charles did create this resource for the community. So there's a bunch of us here that are working. We do review papers, and when we do it, it's always to try to, be supportive and provide people with feedback to make their papers stronger and stuff like that. And you're welcome to email me, if you have questions or concerns. And scorn or ridicule is never, that's just not, the whole point of this is because this all happens in private. So it's all, it's all about helping strengthen our community.
There's a note here from James Freeriks. One concern I have is when quantitative analysis is applied to too small samples. How small is too small? And when is it valid to try to do quantitative analysis? This becomes increasingly important as the work goes to more advanced classes with fewer students. And then Charles said, thank you, Tim, for a great presentation. But can you address it? I actually think it's very important.
Yeah, I think it's a great question. And I don't think there's too small. I mean, it's true that when the numbers are really small, you can't really estimate your standard deviation very well. Right. So, if you have 4 people, it doesn't make sense to talk about the standard deviation of that. So, your uncertainties become really large. And so you're only going to be as sensitive statistically to bigger effects. But I mean, one thing that's like super important, just because you don't have like statistical evidence, because n is small, that doesn't mean that it's not interesting. Right? Big error bars are not a problem. Uh, we get excited about this value of p less than 0.05 or stuff. That's only looking at one alternative hypothesis that it's a statistical fluctuation. Like there are so many more important ones. Like somebody said earlier, like, oh, it's later in the semester and the students have all, are under more stress and so they're doing worse, or they've adjusted to college so they're doing better, and it's not really about our thing. So that's why I said lies, damn lies, and statistics is like, I think like they're a useful tool, but I think it's easy to overinflate them and say, oh, I got a small p-value, I've proved something is correct. Because Eugenia told us, no, we can't prove something is correct. We can prove something is wrong, like that model doesn't work, but I'm sure there's a simple adjustment to that model that then will fit with the data. So I don't know. Did I answer your question?
Yeah, David Meltzer also commented, the uncertainty rises as the sample size decreases. At a certain point, the uncertainty is larger than any projected effect that could be observed. And then Brent is thanking you for a really informative presentation. And I think we all thank you for a wonderful presentation that focuses on the main points of a quantitative paper, not the little details of which test you should do, but like fundamental stuff. Thank you, Tim.
Yeah, thanks. And that reminds me, Eugenia, I was supposed to say this at the beginning. This is also like when we do the reviews, these are the things like it's almost never like, oh, you need to do some esoteric test that we've never seen before. It's almost always about what conclusions that you can make from the statistics. That's almost always the issue.
Well, I want to thank everybody for showing up for tonight's community conversations, and to remind you that our next community conversations will be January 8th. Is that correct, Eugenia? Is that right?
Yes.
Yes, and it will be Ben Van Dusen and Jason Neeson, and
we will
Eugene
announce it. We will announce it.
We will announce it soon, and we will also in January having a virtual PERTG town hall. We'll also be talking and getting feedback from the community, and which has been very valuable for when we plan these community conversations. So once again, thank you very much, and have a great Thanksgiving.
Thank you.
Bye.